First of all, I would like to thank you thank the organizing committee and Jeffrey to give me the opportunity to present the work today we've done in the lab recently. And I'm going to talk about the two-pore domain potassium channels and their implication in the pain and how we can remote control pain by controlling their activity with light. Migraine is a neurological disorder which affects around 20% of the adult population in the world. And if you are a woman, the prevalence is 3 times more important. And the mechanism underlying the migraine are not very well understood, but something that is well admitted in the field is that when you have an hyperexcitability of the neuron innervating the face, the trigeminal neuron, the sensory neuron, you will trigger the migraine. The chronic pain is also related to an increase of the excitability of the sensory neuron, either from the face, the one which are called the trigeminal neurons, or the one which are innervating the rest of the body, which are called the dorsal root ganglion neuron. The excitability of this neuron are under a control of a current which was described during the 50s by Huxley and Huxley, which is called the leak or background current. And in 1995, in yeast, it was shown to be carried by Steve Goldstein by the two-pore domain potassium channel, then in 1996 in France by Lazinski in mammals. These channels are called the two-pore domain potassium channels because each subunits which are composing this channel possess 2 p-loop. As you need 4 p-loop to form a functional channel, these channels are not active as a tetramer like a checker channels, but they are active as a dimer. When they are open at rest, they allow the selective transport of potassium ions from inside to outside the cell because the potassium is more concentrated inside. And as the potassium is positively charged, this induces an hyperpolarization of the cell, and therefore the cell stops to fire when these channels are open. If you have a stimulus that will hit the channel, this will induce the closing of the channel, and what you will get a depolarization and an increase of the cell excitability. 15 genes in humans have been found to encode for this potassium channel family that we can class in 6 subfamilies, but today I will focus on the ones which are expressed in the nociceptors. The ones which are expressed in nociceptor are the task channel member, task 1 and task 3, the TREC channel member, TREC 1, TREC 2, and TRAC, and TRESC. And the importance in the migraine was shown recently in 2010 by a publication of a mutant, which is called the TRESC-MT mutant, which is correlated to migraine in a large pedigree. Later on, we discovered why this mutant was able to induce migraine. This mutant was able to induce migraine because he was able to inhibit specifically TREC 1 and TREC 2. And this is because it inhibits TREC 1 and TREC 2 neurons that is induced an increase of the neuronal excitability that will lead to migraine. Normally, if you want to study the function of a channel or receptor, you will use pharmacological agent coming from the nature that will bind on the channel under investigation, and you will have an effect, and depending on the effect, you will determine the function of the channel under investigation. Sometimes you don't have ligands, and even if you have a ligand, it's really hard to get a spatiotemporal resolution in the effect. When you apply the ligand in the animal, you cannot wash it out, meaning you apply it one time, and you cannot determine when and where it will be active. Therefore, to palliate the fact that you don't have a ligand, for example, another strategy came from the invalidation of the gene, meaning you invalidate the gene in the animal, and you will look at the phenotype, and you will determine the function of the gene under investigation. You can also use conditional knockout to gain a little bit of spatiotemporal resolution in the effect, but it's kind of low. Therefore, we have decided in the lab to create a new pharmacology on these channels, on the two-pore domain potassium channel, what will be the light. Why is the light? Because the light can be applied instantaneously. The effect you will see can be reversible, and it's not invasive. And in addition, you have like the spatiotemporal resolution given by the beam of light. But first, how to gain the light sensitivity on a receptor or channels? You have to use a molecule that will feel the light. And the first strategy, we will use a phototethered ligand, which is called MAC. MAC is made of a monoamide function, which allows to anchor the molecule covalently on an engineered cysteine, which has been placed at the vicinity of the pore of the channel. This is the potassium ion. This is the cysteine, which has been introduced. You have the azobenzene part, which will feel the light the photon will hit this azobenzene part. This part is in a trans state, in a dark or in a visible light. But when you shine a light at 380 nanometers, you will shift from the trans state to the C state. That will remain stable for a certain amount of time. You can speed up the process to go back to the trans state if you give a pulse of light at 5 nanometers now. Meaning you can bend and unbend the molecule just by giving a pulse of light at 380 nanometers or 500 nanometers. And finally, the Q is for quaternary ammonium. It's just a pore blocker that will go within the pore of the channel and will block physically the flow of potassium through the channel. This is how TREC light is working in the dark or in a visible light, TREC light give a normal TREC 1 current. But now when you shine a light at 380 nanometer, you stop the function of the channel, but you can go back to a normal function if you give a pulse of light at 500 nanometers. And you can do it again and again. It's not use dependent. Using this strategy, we have been able to show that TREC 1 is involved in the GABA-B response in the hippocampus. In fact, when you activate the GABA-B current using the baclofen, the specific agonist of the GABA-B receptor in the hippocampal neuron, you have an outward current that appears. You have a part which is constant, which is related to the activation of GERT, which was known for like 20 years. And in addition of that, you have a current that follows the light, close in UV and open in the green. This current represents around 25% of the GABA-B current, and this is linked to the activation of TREC. The cool part of this strategy is that you can go back and forth, meaning if you have a small effect, you can see it. You cannot do that when you start to change your perfusion system. Therefore, this technique, in this essay, we have shown that we can modify TREC 1 to be light sensitive, but in reality, you cannot use TREC light as it is to study the function of TREC 1. In fact, if you transfect TREC light, the expression of the channel at the surface of the cell will be largely higher as the density you can have under physiological conditions. This is the reason why we have used a trick. We have used an animal model, which is called Star Trek. Star Trek is an animal model. It's a knocking mouse in which we have replaced the wild-type TREC 1 gene by its ligated homologue. This means that this mouse behaves like a normal mouse, but when you want and where you want, you can close the channel and look at the function of the channel. This strategy is really nice, but as you see, you need a genetic manipulation, and it's long and costs a lot of money. This is the reason why we have decided to develop another strategy. We have decided to use a photochromic ligand, meaning we have to use a ligand which is soluble. But to use this technology, first of all, you need to have a ligand that you know that will bind on the channel under investigation. It was the case in our condition because we got the ML335, which is an antagonist of TREC 1 and TREC 2, the channels that we are working on. If you look at the structure of this molecule, you have some rings which are linked by an amide link. And what we have done, we have replaced this amine link by a dinitrogen bound. And now you have this molecule. And as you may see there, you have an azobenzene function, meaning this molecule now can feel the light. This molecule in the ambient light or in a dark will be in a trans state. But now when we shine the light at 380 nanometer, you will shift to the C state that will remain stable over the time. You'll be able to be back to the trans state by a pulse of light at 500 nanometers. And what you hope that one of the configuration will have a certain affinity for your receptor under investigation, and the other one not. It's what we have tested first in heterologous system on TREC. At the beginning of the experiment, we apply the drug, we have no effect. Then we apply the green light, no effect. Then we shine the UV light, and we got up to 80% of the inhibition of the current carried by TREC channels. This current is very relatively potassium because if you plot the density of this current according to the membrane potential, you have a perfect outward current, a perfect potassium current related to TREC. What about now the specificity of this molecule? In fact, in human, close to 80 genes are encoding for potassium ions. You have the voltage-gated potassium channels, the inward rectifier channels, and also the two-pore domain potassium channels. Therefore, we have tested the several families to be sensitive to this lucky molecule, and we found that any of the shaker or the KIR channels were sensitive. In fact, as you may see there on an example for the IKS current carried by the Cassian Q1 subunit associated with Cassian E1, you may see that you have no regulation of the current by the light. What about now the specificity within the family? I remind you that six of these channels are expressed in trigeminal neurons and in dorsal root ganglion neuron. We therefore tested this channel to be sensitive to LACI. What we found that as TREC 1 and TREC 2 were highly regulated by the light in the presence of LACI, but we have been very lucky because task 1 and task 3 were not. Meaning, what we got a molecule which was able to modify specifically the activity of TREC 1 and TREC 2, the one which are involved in a migraine and the chronic pain. Now, the next step was to determine what will be the specificity of this molecule in native tissue. Therefore, we went back to our trigeminal neurons and we look at the effect of the molecule and the light on this neuron. We did exactly the same experiments in the heterologous system. First, we apply in this neuron the drug. We didn't observe any effect. We apply the green light. We didn't observe any effect. And then when we shine the UV light, we were able to see a current which is stop in UV, open in the green, stop in UV, open in the green. If you look at the amplitude of this light-gated current according to the membrane potential, you can see that you cross the x-axis at minus 80 millivolts, the expected potential in our condition for potassium, meaning we know that in native tissue, we block specifically potassium ions, potassium channels. Now we want to know what are the channels which are carrying this current. And to address this question, we have used a double knockout neurons, in which we have invalidated TREC 1 and TREC 2. If you invalidate TREC 1 and TREC 2 in trigeminal neurons, you can lose 80% of the light-gated current. In addition, if you transfect the dominant negative form of TRESC in this neuron, you lose the 50%, the 30% remaining current. Meaning, in our conditions, in these experiments, on the trigeminal neurons, we specifically block TREC 1, TREC 2, and TRESC, the channels which are involved in chronic pain and migraine. Therefore, now we have a tool to study the function of this channel physiologically. And first, we have been looking at the nociceptor in trigeminal neurons and also in DRGs. In trigeminal neurons, when you shine the UV light, as you may see, you can trigger some action potential. This means that the acute closing of TREC 1 and TREC 2 and TRESC is sufficient to induce an increase of the excitability of nociceptors from the face, innervating the face. What about the ones which are innervating the rest of the body? We observe exactly the same effect. When the light was shined on UV, you can see that you can trigger a huge amount of action potential. Therefore, with this technique, we can remote control the nociceptor activity. But what about in vivo? Can we remotely control TREC 1 in vivo, TREC 2, and TRESC? And can we control the pain in vivo in a freely moving animal? To respond to this question, we have injected 15 microliters of LACI1 in the paw of the animal. And then we have shined the light on it, and we have tested the mechanical pain with the paw withdrawal threshold and also the thermal pain. At the beginning of the experiment, we injected LACI or we injected the saline solution, saline and LACI. As you may see, the injection of LACI didn't modify the sensitivity to the animal for the mechanical pressure. What we have done, we have done a Van Frey test. A Van Frey test is when you take filaments, you put pressure on it, and you look at how many pressure you have to put to induce the withdrawal of the paw of the animal. And now, if you look closely after 20 seconds of UV light, meaning we injected the animal, after an hour, we shine the light for 20 seconds, and after we made the test. As you may see, we have a 5-fold decrease of the paw withdrawal threshold. Now the question, is it reversible? Meaning, can we reverse this hypersensitivity? The response is yes. Because if you wait 5 minutes, the time for the molecule to relax, to be back from the cis, from the trance state, as you may see, you are able to recover. You can do it again. You can do a new cycle by putting another pulse of light for 20 seconds. I have to say that the lamp we used to do this experiment cost $20. It's from eBay. And you can do it again and again. And it works all the time. What about now the thermal sensitivity? What about the thermal pain, the allodynia? We did exactly the same experiments, but now, oh yeah, sorry about that. Sorry, I just forgot these things. This is nice, but this doesn't show that it is related to TREC channels. To respond to the question, is it related to TREC channel? The response is yes, because if you knock down TREC 1 and TREC 2, we are no longer able to induce the pain in this animal using the light. This shows that acute closing of TREC 1 and TREC 2 in vivo is able to induce pain, mechanical allodynia. And in addition, this shows also that the channels are localized at the terminal nerve endings. Why is that? Because the UV light cannot penetrate deeper than 600 micrometers. And the only neurons you can find at this distance of the derm are only the pain receptor, the terminal nerve endings. What about the thermal sensitivity? We did exactly the same experiment. At the beginning, you can notice that there is no effect of LACI in the dark. But when we shine the light at 380 nanometers for 20 seconds now, we have an hypersensitivity of the animal, meaning the PO withdrawal latency, because this time we didn't look at how much pressure you have to put on the PO, but we looked at how long it takes for the animal to withdraw his PO when you have a stimulus which is 42 degrees Celsius. And at the end, if you wait 5 minutes, again, you are able to go back to normal. And if you do again a pulse of light, again, you are able to induce an hyperalgesia that will be reversed. For how many times can you do the cycle? For how long can you do this type of cycle? You can do it for a week after one injection. If you inject 1 time the mouse during a week, you can produce pain just by giving a pulse of light at 480 nanometers. That is kind of cool. Therefore, we can say that linking pain excitability in a non-invasive manner and in a reversible manner without the need of any genetic and any various manipulation. And as you may know, the chronic pain is something which is largely, which has been conserved during the evolution. Therefore, we wonder, can we remote control the pain in inferior animals? And we have chosen the C. elegans for several reasons. First of all, the C. elegans is transparent, meaning it's compatible with optopharmacology. And second, the C. elegans possesses 40 key-to-peak domain potassium channels. What we have done at the beginning, we incubated our animals for 30 minutes in the dark, in the presence of 50 micromolar of LACI1. Then we shine the light at 365 nanometers to activate the molecule. And then we shine the light at 480 nanometers to stop the function of the molecule. And this is the movie you can have. At the beginning of the movie, you can see they are swimming normally. They crawl normally in their dish. Now, I will shine the light at 365 nanometers in a few seconds. You will see the up now. And as you may see, they change their behavior. What do they do here? They try to escape. It's an escape behavior, which is called an omega turn. But they cannot escape because the light is everywhere, meaning they never stop to turn. And everybody is doing the same. Huh? And now, you see, the light is 480 nanometers, and everybody is back to normal. And you can do it again and again. And it's very related to the activation, to the inhibition of the 2-pore domain potassium channels, because you are able to inhibit this phenomenon by if you give like an ML367, which is a molecule which is an agonist of the 2-pore domain potassium channel. We propose also to use this technique to develop an high-throughput screening to test for to discover new analgesic drugs. In fact, if you do this test and you look at how many omega turn you will get during a certain period of time, and if you add some, for example, ibuprofen or nefopam or paracetamol or anandamide, you will reduce the number of omega turn. And the more powerful will be your analgesic, the less omega turns will do your animal. Therefore, you can go back from the cell to the IPS, but now you can go also directly in vivo for Sofiane. If you're interested, I am interested also to work with you on this. Therefore, as I told you, we have been able to develop a molecule allowing to study the function of the 2-pore domain potassium channel. This molecule allows us to determine and to demonstrate that the 2-pore domain potassium channel are localized at the vicinity of the epiderm, at the level of the nerve endings, and their acute closing is sufficient to induce allodynia or hyperalgesia. Furthermore, this can be used as a new model to study the pain, in fact, because you can induce pain at the demand, meaning if you have to test a drug, for example, for 30 days, your animal doesn't have to suffer 30 days. You just have to suffer 5 minutes per day, the time to make the point. And after, it's back to normal. And this is without any delay, meaning you don't have to house, you don't have any housing, meaning you receive the animal, you inject it, it's done. You can work. Without any genetic, because there is no genetic inside, and any surgery, because it's just an injection. And in addition, we propose also to use this tool to develop an high-throughput screening test using a full animal. Therefore, I show you two possibilities to remote control the activity of your channel or receptor under investigation. The first one is a phototetheryl ligand. This means that you have to use genetic to be able to use it. And the second one is cool because you don't have to use genetic, but you need to have a ligand to start your experiment. Without ligand, you cannot do this kind of experiment. I will finish on the picture of Antibes that some people know. Antibes is 2,600 years old. And as you may see on the back here, you have the Mont Gelas, which is a peak at 3,200 meters above the sea, meaning you can ski and swim the same day if you like to. And this is where is localized my lab. And if you want to apply for a postdoc, you are very welcome. And I would like to thank also all the people from the lab, especially the giant guy, Arnaud, who did all this part of the work, and also all my collaborators, especially also Michael Kinzer, who did the molecule, who is our super chemist and super efficient. And I would like to thank you for your attention.